Okay, so now we're going to talk about the ideal gas laws, and what we have seen is that there's a relationship between volume and pressure. You know, volume is directly proportional to 1 over pressure. Volume is directly proportional to temperature. Of course, that assumes Kelvin. Volume is directly proportional to the number of moles. If I combine all these, I get NT over P is directly proportional to V. And if I want to replace this proportionality constant, I need to find a constant that makes that equation true. And that constant is known as my ideal gas constant, capital R. Okay, so depending on my units for pressure or volume, my R units change. Now, the two that you need to know for the AP exam, they're both on the sheet, but again, if you're taking the multiple choice, you won't have that sheet. So basically, most of the gas law problems use this, 0.08206, and it's liters atmospheres over mole K. Now, if you are dealing with energy, if you need joules, if you're dealing with energy, the R will switch to 8.314. Okay? Now, what you need to always make sure of is if you're using this 0.08206, that you have your volume in liters and your atmospheres, your pressures in atmospheres, and of course you have temperature in Kelvin, because you would never think of not doing that. So we end up with this equation, as you know, is PIV, PV equals nRT. Alright, so let's go ahead and use our PIV. Okay, so let's just pause here for one second. Okay, so calcium carbonate decomposes upon heating to give calcium oxide and CO2. We have a sample of calcium carbonate. It is decomposed, and the carbon dioxide is collected in a flask. After the decomposition, the gas has a pressure of 1.3 atmospheres and temperature of 31, and we want to know how many moles of gas. Okay, so we can use PIV for this. PV equals nRT. I want to solve for moles, so moles, if I divide both sides by PV, I get, or divide both sides by RT, I get moles is PV over RT. So let's fill in what we know. So we know this is 1.3 ATM. We know volume is 250 milliliters. Now I need that in liters in order to use my R of 0.08206, right? Because that is liters atmospheres over moles K. Okay, 1.3. So this is 0.250 liters over my R, which is 0.08206 liters atmospheres over moles K, times my T. Now my T is 31 Celsius, and if I add 273 to get to that, I get 304 K. 304 K. So my K cancels there. My atmospheres and liters will cancel on, end up with units of moles. Okay? So if I punch this, I'm going to get 1.3 times 0.25 equals, divide by, in parentheses, 0.08206 times 304, close parentheses, and I get 0.013 moles of CO2. And it looks like I want two sig figs, 0.013 moles. Okay, let's take a look at another. Okay, a gas pressure in an aerosol can is 1.5 atm at 25 C. Assuming the gas inside obeys the ideal gas equation, what would the pressure be if we heated the can to 450? Okay, so it talks about the ideal gas equation, but in fact that's not really what you need here. What we have is change in conditions. We're starting at 1.5 atm at 25 degrees C, which is 298 K. And we are heating it up to 450, which is 273. So this is really a gas law problem, not a PIV. So that's 723. It goes up to 723 K. And wants to know what's happening to my pressure. So all I have to do is take my pressure of 1.5 atmospheres. And these laws assume ideal behavior, right? Which is what it's really talking about here. So if my temperature goes way up, my pressure will go way up. So I want a factor to make it go up. And that's going to be over 298 K. And if I punch all this, I end up with 1.5 times 723 divide by 298. Oops. 298, and I get 3.6. I want 266. 3.6 ATM. Pressure goes way up. Okay, so some of the common problems on the AP exam are density problems. And the key, I think, to get density problems, or think of density as, remember that we're usually talking about grams per liter. So when you're given density, you're given your volume, which is 1 liter. Okay. And if you get a problem where it tells you to identify the gas, the way you identify any substance usually is by finding its molar mass. Okay. All right, so let's take a look at some. So what is the density of carbon tetrachloride vapor at 714 torr in 125 C? Okay, so density is going to be grams per liter. Liters is 1, right? I don't know grams, so let's think. PV equals nRT. I have pressure. I have a pressure. I have a temperature. I have a volume. I have a gas constant. If I solve for moles, I should be able to figure out density, because I know volume is 1 liter. Okay, so N equals PV over RT. And my pressure is equal to 714 torr. So I'm going to convert that to ATM. 714 torr, and what I know is 760 torr is 1 ATM. So if I punch that, I get 714 divided by 760 gives me, alright, so let's put that there, 0.93, and I'm going to carry as many sig figs as is reasonable, because we always want to round at the end, times my volume. My volume I'm going to assume is 1 liter, right? This is ATM. My R is 0.08206 liter atmospheres over moles K. And my T is going to be, it's 125 C. If I add to that 273, I get 8, 9, it's 398. K. My K will cancel, liters atmosphere will cancel. I'll end up with units of moles. And when I do that, I get, let me see, 0.9. Let's do this. Let's go up. I pick that up. Never mind. That was not as easy as I thought it was going to be. Alright. I'm going to clear that. And I'm going to enter 0.93947 divide by, in parentheses, 0.08206 times 398, close my parentheses, and I get 0.0286765 grams of carbon tetrachloride. Okay. And what I know is there are molar mass of carbon tetrachloride. Carbon is 12.01. Tetrachloride, that's chlorine times 4 times 35.45. So let's figure that out. So 4 times 30, oops, 4 times 35.45 equals plus 12, oops, 12.01 0.01 equals, so my molar mass is 153.61. Okay, I'm sorry. This is not grams, this is moles. So I have that many moles, and what I know is 1 mole of carbon tetrachloride is 153.61 grams. So I multiply 153.61 times my 0.028765, and I get 4.41 grams, and we said 1 liter is what we're starting with, grams per liter is my density. Okay, so the density of a gas was measured at 1.5 atm, 27 C, 1.95 grams per liter. We want to find the molar mass. Okay, so again, PV equals nRT. If I find my N, that should lead me to my molar mass. Okay, so N is PV over RT. P in this case is 1.5 atm. V is, I'm going to assume 1 liter, right? Grams per 1 liter. My R is 0.08206. My T is 27 plus 273, that's 300 K. Okay, so what I have, I'm going to clear this, and I get 1.5 divided by 0.08206 times 300, close my parentheses, and I get 0.0609 grams. I'm sorry, I get 0.0906 moles. Okay. So if I have 0.0609 grams, now molar mass is grams per mole, right? So if I take my grams, which I was given here, 1.95 grams, and I divide it by how many moles I have, divided by 0.0609 moles, I get 1.95, whoops, divided by, and I'm just going to go up and pick up this number, divided by that number, equals 32 grams per mole. Okay, and I bet you can figure out what gas it is if it says it's a diatomic gas, and it would be oxygen, right? Alright, 1 mole mass of a gas. Alright, series of measurements are made to determine the molar mass of an unknown gas. This is actually a nice problem for stoic and everything else. Okay, I'm just doing a bunch of stuff we've learned about. Okay. Alright, so a series of measurements are made to determine the molar mass of an unknown gas. First, the flask is evacuated and found to weigh this. It is then filled with a gas to a pressure of that many torrs, 31 degrees. It is reweighed, and this is its mass. So this tells us the mass of the gas. So let's figure out the mass of the gas. It's going to be 137.456 grams minus empty 0.567 grams. This is going to be let me see, 2.889 grams of gas. Okay. Alright. It is, find the flask is filled with water at 31 degrees C and found to weigh 1067.9 grams. Okay, so, and the density of water is this. So this is going to allow us to figure out the volume of the container. So what we know is the flask empty weighed this, and the flask filled all the way with water weighs this. And if we know the mass of the whole thing of water and the density, we can figure out the volume. So let's do that. So this is 1067.9 minus the flask empty, which is 134.567. And if I subtract those, I get 933.33 grams of water. And what I know from this density is there's 0.997 grams in 1 milliliters. Now I'm going to have to get this to liters, but let's just do this. I'll put one more factor there. It says 1,000 milliliters is 1 liter. And this is going to give us 0.9361 liters. Okay. So we know the mass of the gas, we know the volume, we know the pressure, we know the temperature. Okay, we want to know the molar mass. Okay, so we're going to do N equals PV over RT again. Pressure is 735 torr, so I'm just going to leave that at 735 divided by 760, right? That will give me ATM. Pressure times my volume is 0.9361 liters. And my R is 0.08206 liters atmospheres over moles K. This is atmospheres here. And my K is 31C. 31 and 273 is 304. So that's 304. All of my units will cancel. Liters atmospheres. I'll be left with moles. And the number of moles will be, let's punch it. So 735 divided by 760, first to give me the atmospheres, times 0.9361 liters equals, I'm going to divide that by, in parentheses, 0.08206 times 304, close the parentheses, and I get 0.03629 moles, okay, of this gas. Okay, and I have this many grams, so again, let's do it up here. Molar mass is grams over moles. I have 2.889 grams. I have 0.03629 moles. So let's divide this. I'm going to get 2.889 divided by 0.03629 equals 79.7 grams per mole. Looks like that agrees with the answer. Okay. Alright, so we're going to do a little bit of gas stoichiometry. So remember, we can go from mass to moles using the molar mass. We can go from moles to number of particles, atoms, or molecules using Avogadro's number, 6.02 times 10 to the 23rd. Hopefully it's sort of ingrained in your brain now that molarity is moles times volume, or moles over volume. So moles is molarity times volume. So I can go back and forth between moles and molarity. But the one that we're going to focus on mostly here is if I'm at STP, I use the molar volume. 22.4 liters is 1 mole of any gas, right? And if I'm not at STP, I have to figure out my volume using Pevner. PV equals nRT, or V equals nRT over P. Okay, so here we have safety airbags. And automobiles are inflated by nitrogen gas generated by the rapid decomposition of sodium azide. Okay, if an airbag has a volume of 36 liters It's filled with nitrogen gas at a pressure of 1.15 atm, temperature of 26. How many grams of sodium azide must be decomposed? Okay, so this is a stoich problem. It's a stoich problem and it's a Pivnert problem. So I first have to figure out how many moles of this I have. And once I know how many moles of this I have, I can use stoich to figure out how much of this I need. Okay, so I have, let's figure out N equals PV over RT to get the moles of nitrogen gas. My pressure is 1.15 atmosphere. My volume is 36 liters. I'm going to put that over 0.08206 liters atmospheres over moles K times 20, this is still over, times 26 C, which is 299 K. Okay, my units will all cancel. So if I punch this, I'm going to get 1.15 times 36 equals, divide by 0.08206 times 299, close my parentheses, and I get 1.687 moles of nitrogen. Okay, and based on this I have to figure out how much sodium azide I need, how many grams of that. So what I know is there are, from the stoichiometry, is there are 3 moles of nitrogen come from 2 moles of sodium azide, and I also know that this is moles, 1 mole of sodium azide has a molar mass of nitrogen's 3, so let me see, that's 14.01 times 3 equals plus 22.9 is sodium 99. That's my molar mass, okay? And this is 65.02. Alright, so let's plug and chug. So I got 65.02 times 2 times 1.687 equals, divide by 3, keep your fingers crossed, and we get nice 73 grams of sodium azide. And it looks like I want 3 sig figs. Okay. Alright, quicklime is produced by the thermal decomposition of calcium carbonate. Calculate the volume of carbon dioxide at STP produced from the decomposition of 152 grams of calcium carbonate by the reaction. Okay, so this is pretty straightforward. Looks like I have a balanced reaction. So I'm starting with 152 grams of calcium carbonate, and once I know how many moles of that I have, I can use a stoich and figure out how many liters of carbon dioxide I need, right? It's all at STP, which makes this really simple. So I got to figure out the molar mass of calcium carbonate, so let's do that. So 3 oxygens is going to be 48 plus 12.01 for carbon, plus calcium is 40.08. That's a molar mass of 100.09. Okay, grams of calcium carbonate is 1 mole of calcium carbonate, and I need 1 mole of calcium carbonate to get 1 mole of CO2, and 1 mole of CO2 is 22.4 liters of CO2. So I'm just going to do a plug and a chug. So it's 152 times 22.4 equals, divide by 100.09, close my parentheses, and I get 34, looks like I want 3 sig figs, 34 point, looks like 0.0 liters. Okay. Alright, sample of methane gas having a volume of 28 liters at 25 C and 165 atmospheres was mixed with a sample of oxygen having a volume of 35 liters at 31 C and 1.25 atmospheres. Mixture was ignited to form CO2 and water. Calculate the volume of CO2 formed at the pressure of 2.5 atmospheres and temperature of 125 C. Okay, so this is a combined Stoich and Pivner problem, and it's limiting reactant, it looks like. So first we're going to write the balance equation. So I'm starting with methane. You should know methane is CH4. Combustion always means add oxygen. We always get CO2 and H2O. Okay, so I need 2 of those, and then I'll need 2 of those. Okay, so it tells me what I've got for methane, so I'm going to start with that. I got to figure out how many moles I have, so it's going to be PV over RT, and this is for methane, so I'm just going to write CH4. So this is going to be, pressure is 1.65 ATM, liters, volume is 2.80 liters over 0.0862 0.082, I am losing it, 0.08206 times my temperature is 25, so that'd be 298. And if I punch that, I get 1.65 times 2.8 equals, divide by 0.08206 times 298, close my parentheses, and I get 0.188927. And it's good to carry as many sig figs as you can, or as reasonable, and then you round at the very end. Alright, so I also have to figure out how many moles of oxygen I have, because it might be limiting. Let's just make sure. So moles of oxygen is going to be PV over RT. Its pressure is 1.25 ATM. Its volume is 35 liters. Looks like it's going to be more. Over 0.08206 for my R times my T. Let me see, the oxygen's at 31, so 31 and 273 is 304. Alright. Pretty sure this is going to be quite a bit higher. Alright, so I got 1.25 times 35. I missed a 5 in there. Alright, let's just punch it again. Times 35 equals, divide by 0.08206 times 304, close my parentheses, and I get, alright, quite a bit more moles, 1.75 moles. This is O2 and this is methane. So I get a whole bunch of O2, plenty of O2, so what's going to limit me is the 0.1889 moles of this, which should give me 0.1889 moles of this, right? They both have a 1 coefficient. Alright, so I want to know the volume of CO2 formed. So in this case, if I take my PV equals nRT, my volume is going to be nRT over P. And in this case, I know I should get this many moles, 0.1, let me just block this off, 889 moles, times my volume of CO2, which, I'm sorry, not my volume, I would need my R here, 0.08206 0.08206 times my temperature, which is 125, so I add 273 to that, and I get 398 times 398, and my pressure there says, whoops, 2.5 atm. What a mess, huh? Alright, so let's punch this and see what we get. 0.1889 times my R, 0.08206 times 398 equals, divide by 2.5, enter, and I get 2.47 liters. Nice. It's always nice when you get the right answer, isn't it? Alright, we're going to stop there and come back to Dalton's laws of partial pressure. Alright.